Hello and welcome to the AICE Chemistry lecture series. In this video, we're going to cover the very last bit of the curriculum we have left. And it's actually no longer in chapter 18. This does not have necessarily to do anything with specifically carbonyl compounds. In this section, we're going to look at organic mass spectroscopy. And this is actually a section, the very last section of chapter 3 that we skipped at the time because we don't learn about organic chemistry and to AICE chemistry at our school. So we have to now go back and look at mass spectra, which is something we actually talked about before, but as it applies to organic chemistry. In the past, in chapter 3, we talked about mass spectrum for isotopes. We talked about how in a sample of an element, we use mass spectroscopy, which uses high energy electrons, to ionize a molecule. We can then use the mass spectra and its curvature and a detection site and magnets and to identify the mass to charge ratio of the different polarized or ionized molecules that we see. So we used again this in chapter 3 to identify isotopes of an element, and you can again go back and look at that. But now we're going to see what happens when we do the exact same technique, but on an organic compound. When we fire high energy electrons at an organic compound, we end up breaking the covalent bonds in an organic compound apart. We use high energy electrons because when we do this, it will knock off an electron from the molecules, creating positively charged particles. So what essentially happens during mass spectra? We have a particle and we'll use, let's say, an alcohol. Let's make it simple as an example. So we'll use here our propanol. So this is one propanol. In mass spectra, what happens is that we grab this sample of a compound and we fire high energy electrons at the compound. And a few things might happen to this compound when we do that. One of the things that will happen for sure is that as a result, and actually let me change the type of arrow I use here. So we're going to make a squiggly arrow. We're going to fire a high energy electron at our molecule. And one of the things that will happen is that that electron will knock off a single electron from this molecule. Not an electron in a bond, but just a single molecule made from the oxygen or the hydrogen, doesn't really matter. So what's going to happen is that that's going to create the exact same molecule, but somewhere in that molecule there will be a positive charge. Because if we get rid of an electron, if the electron we shot at the molecule gets rid of an electron, we are going to end up with the exact same molecule, but with a +1 charge. This +1 charge is what allows mass spectra to work. It's what allows the molecule to be bent by a magnetic field and detected by the detector. Now, because the charge is always +1, the mass to charge ratio that we see, what we call the MZ, which is the x-axis for mass spectra, the mass to charge ratio for that fragment is going to be equal to the molar mass. So the MZ here is going to be equal to the molar mass of the compound. Because remember, that electron that we knocked off, it doesn't really weigh much, right? So we're going to see one of the highest peaks, what we call the M peak, is going to be just our molecule with an electron knocked off. But another thing that could happen is that the molecule could break into a bunch of different ways. So this molecule could break into different fragments. If, for example, and actually let me use a different color here. If we broke the molecule here, for example, what will happen is that we would end up with, depending on which way the electron went, this fragment on the left side, where we have the CH3 with a plus charge, in which case the mass to charge ratio, again, which will be equal to the molar mass of this, will be 12 plus 1 plus 1 plus 1 is 15. Our mass to charge ratio will be 15 because the molar mass of this fragment of 1 carbon and 3 hydrogens is 15. On the other hand, we could also end up with a positive charge on the opposite side, on this side of the molecule, giving us a CCH with the OH and the positive charge on this fragment. The mass to charge ratio, and again, because the charge is always 1, the mass to charge ratio is always equal to the mass of the fragment. So when it breaks and it splits in this side, we end up with 2 carbons plus an oxygen plus 6 hydrogens. That's 24 plus, 5 hydrogens. 24 plus 5 is 29, plus 16 is 45. So the mass to charge ratio for this fragment would be 45. So depending on how what the molecule is and how it breaks, right, we will get different fragments with different mass to charge ratios. Again, this is just one example. That could also break here. It could break here. We could end up with just a CH2. So we're going to get out of this one molecule, this one very simple molecule as far as organic chemistry is concerned, we're going to get a number of different mass to charge ratios. We're going to get what we call the M peak, and we'll look at that in a second, which is the full molecule with just a plus 1 charge, which will have the molar mass of that compound as mass to charge ratio. We would end up with different fragments as the molecule breaks apart in different places that have a plus 1 charge, and giving us, different mass to charge ratios based on the molar mass of that little fragment. So let's go back and look at what these actually look like. So when we do a mass spectra for the for an element, we will see peaks that represent all the different isotopes of the elements. But when we do a mass spectra for an organic compound like the one here, each peak represents a different fragment. Now we're going to get different fragments and different mass to charge ratios, either MZ or sometimes you'll see as ME on the x-axis, and the y-axis will represent the abundance of those fragments. But the abundance is not as important when it comes to organic chemistry. Now, the M plus peak, let's talk about that. The peak with the highest or largest mass to charge ratio is also called the M plus peak, or the molecular ion peak. So when we look at a mass spectra like the one we have here, the highest, the biggest and furthest to the right peak is going to be our M plus peak. That peak represents the molecule when only the single electron is knocked off and it has a plus 1 charge. So here, for this mass spectra, our M plus peak, our M plus peak is right here. So let me highlight that. This peak is at 60. It is the biggest peak and furthest to the right we can see, and it's at 60. What does that tell us? That tells us that this molecule that this mass spectra is for had a molar mass of 60 grams per mole. Because our M plus peak has a molar mass of 60. Remember that M plus peak is caused by the molecule with only 1 electron knocked off of it, meaning it has the exact same molar mass. Since the electrons are relatively massless, that electron being knocked off, it doesn't actually change the molar mass. So here, for example, if we have ethanoic acid, which has a molar mass of 60.04, when 1 electron is knocked off of the ethanoic acid, it creates the exact same molecule but with a plus 1 charge, and that electron gets removed. This essentially fragment, because it is fragment because we removed an electron, is what causes that M plus peak. It's just the molecule. What are all these other peaks? Those are fragments. They're fragments of the molecule that have been broken off as we shoot electrons at the molecule. Because not every single molecule in the example will only have one electron. In this sample, we'll have one electron knocked off. Some of them might actually break apart. So let's look at what that looks like. When an organic compound is hit by that high energy electron, it fragments, is what we call it. Essentially, that fragmentation happens in the same pattern every time we do this. It's predictable. It's always going to look the same. It essentially happens when a single bond breaks in a molecule, and it's going to create smaller, positively charged pieces of that molecule. So here, for example, if we have something like propanone, this compound right here, if we start shooting electrons at this propanone, we are going to fragment it. So if we shoot high energy electrons at this propanone, it might start fragmenting right here. It might break right here in this bond, this carbon-carbon bond. In that case, we're going to get two fragments. A fragment where one side is CH3 and the other side is a carbon double bond oxygen with a CH3. These fragments will have different molar masses. Now, the fragment, when this fragments, it could fragment in two ways. It could fragment where the positive charge ends up with the carbonyl, the carbon double bond oxygen, or it could fragment where the positive charge ends up on the CH3. And both of them will happen. Meaning that we are looking at two different fragments here. We're looking at this fragment, because remember, mass spectra can only identify things with a positive charge. So we have this fragment, which shows up as a peak at, and I believe this is around 43, because the molar mass of this right here is 43 grams per mole. We have two carbons, that's 24, plus an oxygen, which is 16, so that's 40, plus 3 hydrogens is 43 grams per mole. So notice how the peak for this fragment shows up at 43 grams per mole, because that's a molar mass of the fragment. Again, because the charge is plus 1, the mass to charge ratio, or MZ, is a 1 to whatever the molar mass is, in this case 43. On the other hand, when this fragment gets a positive charge, which will happen, they will both get the positive charge in the sample, then we'll get a peak that corresponds to this fragment. A fragment in this case at 15. So right here, which is 15 mass to charge ratio, because the molar mass of this fragment, being 1 carbon and 3 hydrogens, is 15 grams per mole. So every single line you see here, every one of these little lines, every one of the, and we'll talk about this big line in a second, every one of these little lines is a different fragment that comes out of this. Some at 29, some at 27, 26. And then obviously our biggest one towards the end, and we'll talk about this one in a second because that is important. This is going to n+1 peak. But we'll talk about it in a second in the next couple of slides. The biggest fragment, most prominent fragment to the right, is the M+ peak. The one that belongs to the full molecule with a +1 charge when 1 electron is knocked off. The propanone that we're working with here has a molar mass of 58 grams per mole. And so its M+ peak will appear at a mass to charge ratio, an MC, of 58. Now, let's look at some common fragments that we see in mass spectra. Because there are certain combinations of carbon and oxygen and carbon and hydrogen that are very common in organic chemistry. Peaks at 15, for example, are very commonly CH3 peaks. This happens, like we just saw here, when a terminal carbon, like the CH3 here, gets broken off by itself, giving us a carbon with 3 hydrogens. That will have a 15 peak, or a 15 mass to charge ratio. If we see a peak at 28, that is more than likely either a carbonyl, carbon double bond oxygen, or a C2H4, so C2H4 peak, where we have 2 carbons and 4 hydrogens. So either of these will give you a peak at a 28 because they both have molar masses of 28. A molar mass of 29 is usually the result of a 2-carbon fragment coming off. So if we have CH3, CH2, that'll have 2 carbons with molar mass of 12 plus 5 in total, 3 and 2 from the hydrogens. That's 24 plus 5 is equal to a molar mass of 29 grams per mole. So a peak at 29 is usually indicative that there's somewhere in the molecule a CH2, CH3, 2-carbon part of the chain that is terminal. And then some of the bigger ones are things like 43. And 43 is important because of 2 reasons. 43 could be a 3-carbon section, like we have here. So a CH2, CH2, CH3. So this will tell you that you have a 3-carbon section terminally at the end of this carbon chain, because that will have a molar mass of 43 grams per mole. Or more importantly, a lot of the time when we see this 43 peaks, they can be what we call methyl carbonyls, meaning that we have a carbonyl group, the carbon double bond oxygen, with a CH3 attached to it and the positive charge on the carbonyl. This also has a molar mass of 43 grams per mole and is very commonly seen as a peak at 43 in the mass spectra. So just be aware of these. Like, these are different because you will be asked to identify what has made certain peaks on the mass spectra, and all you got to make sure is that what you're identifying, the part of the molecule you're identifying, has the same molar mass as the mass to charge ratio on the peak that you're looking at. Now, like I said earlier, there is usually going to be a very small peak, 1 up from the M plus peak. So we can see here, right? We have that M plus peak right here, and I'll actually cover that with my box, my red box here. But the M plus peak is right here at, I believe this is around 24, 46, or 45, around there. I think it's 46. And then right next to it at 47, so this right here is 46. At 47, we have another peak. Oops, I put those in the wrong place. So this is 46 right here. The M plus peak is 46. And then right at 47, 1 up from the M plus peak, we have another very tiny peak that we call the M plus 1 peak. And again, M plus 1, very obvious, right? M plus 1 meaning that it is 1 up from the M plus peak. That peak, having 1 more mass, corresponds to a different isotope of carbon. Now, the peaks that we usually see have carbon 12 in them, right? These big peaks that belong to part of the molecule, those are carbon 12 containing peaks. But roughly 1.1% of all the carbon in the universe is actually carbon 13. As the names imply, and if you remember isotopes, carbon 12 has a mass number, and usually a molar mass, of 12 grams per mole. Whereas carbon 13, having 1 more neutron, has a molar mass of 13 grams per mole. Meaning that if we were to switch out a carbon 12 for a carbon 13, we would add 1 to the molar mass. So this compound, or this fragment, should I say, for example, we discussed already, has a molar mass of 15 grams per mole. If it has carbon 12 in it. If I were to switch out that carbon 12 and make the exact same fragment, but this time with a carbon-13 isotope, this would now have a molar mass of 16 grams per mole because of that extra neutron. This is where the n plus 1 peak is important. The n plus 1 peak is going to essentially be counting all of the compound, all the whole molecule that has at least one carbon-13 in it. And that's going to be around 1.1% of molecules of any organic compound are going to be containing one carbon-13 atom. Because of that, their molar mass is a little larger. We can use that ratio, that 1.1%, to actually figure out how many carbons a compound has. Because, let me erase this right here. The difference between these two, and this is ethanol, so the difference between the M plus peak here, which is for ethanol, where both of the carbons in the ethanol are carbon-12, that molar mass for that ethanol is going to be 46. But right next to it, that little tiny N plus 1 peak, that N plus 1 peak is for an ethanol molecule, or the ethanol molecules, that have carbon-12 for one of the carbons, but the other one is carbon-13. And we actually know the exact ratio of these. We know that these are going to be 1.10% of all these ethanol molecules in the sample or in the universe, whereas this is a 47, is a 47 grams per mole. Because of carbon-13, the molar mass is going to be one higher. But the one with the carbon-12 is going to be 98.90% of all of the molecules of ethanol in the universe or in the sample. So this ratio actually helps us figure out the number of carbons in a molecule sample. So if we got these mass spectra, we can actually do this calculation right here to calculate the number of carbons, N. Let me put that here. N is the number of carbons in the molecule. So N is the number of carbons in our molecule. How do we figure out N? If we do 100 divided by 1.1, because 1.1% of all the carbons are carbon-13, times the abundance of the N plus 1 peak over the abundance of the N plus peak, that's going to give us the number of carbons. Now, another way to say abundance is our y-axis. So instead of abundance, we can say height. So the height of the N plus 1 peak divided by the height of the N plus peak times 100 over 1.1 gives us the number of carbons in our compound. This is something that is a really easy point to score if you remember the equation. If you don't remember the equation, you're never going to get the answer. But most of the time, we don't even have to guesstimate or guess what the heights are. They will tell you in the question what the height of those peaks is. And then all you have to do is remember the equation, divide, and then times 100 over 1.1 to get the number of carbons as a whole number. Now that's N plus 1 peak. In certain molecules, specifically molecules with chlorine or bromine atoms, essentially halogen alkanes, you are going to see peaks even further to the right of the N plus 1 peak. And we call these N plus 2 and N plus 4 peaks. And what are these going to belong to? Just like with the carbon with the N plus 1 peak belonging to an isotope of carbon, when we have chlorine and bromine, we are going to have what we call N plus 2 and N plus 4 peaks because of the isotopes of chlorine and bromine, which are very prominent. Why is this? There are 2 chlorine isotopes and there are 2 bromine isotopes that can exist. And they have very specific and very large percentages in the universe. Chlorine has 2 isotopes, chlorine 35 and chlorine 37, which are off by 2 neutrons, therefore the n+2 peak. And they have a 75 to 25% ratio, meaning that out of all of the chlorine in the universe, 75% is chlorine 35, and out of all the chlorine in the universe, 25% is chlorine 37. Bromine, very similarly, has 2 isotopes that are 2 away from each other, 2 neutrons away from each other. So bromine 79 and bromine 81, again, 2 away from each other. But they actually exist in a 50-50 ratio, in a half and half ratio. So if there is a compound that contains either 1 chlorine or 1 bromine, because of the +1 or +2 difference in the isotopes, you're going to have a peak at n+2. So just like the 1 came from the carbon 13 having 1 more neutron than carbon 12, the n+2 comes from the chlorine 37 having 2 more neutrons than chlorine 35, or bromine 81 having 2 more neutrons than bromine 79. But if there are 2 chlorine atoms or 2 bromine atoms, meaning that we have, we have a dibromo or a dichlorohalogenalkane, then there's going to be a peak at n+4. The n+4 peak is only going to be present if there are 2 of those atoms, not 1. And that will represent when there are 2 of the higher isotope in the molecule. So if we have 2 of either halogen, we can have 3 different combinations of isotopes which are present. The n+, the n+2, and the n+4. So let's do chlorine first, right? So chlorine being the n+, that will be, if we have 2 chlorine atoms, 2 chlorine 35 atoms for the n+. So if we have a molecule with 2 chlorine atoms that are both 35, that will be our n+ peak. If the molecule had 1 chlorine be chlorine 35, but the other one be chlorine 37, then there will be a peak 2 up from the original n+ peak, meaning that will be n+2. That's where the n+2 peak comes from. One where we have a 37 chlorine and a 35 chlorine. And then if we have a molecule where both of the chlorines are chlorine 37, that will constitute the n+4 peak. Now you might be thinking, why can't we have carbons where there's more than 1 carbon 13? And really it is that you can, but look at the percentages. Carbon 13 constitutes 1.1% of all carbon, whereas carbon 37 constitutes 25%, and bromine 81 constitutes 50% of all chlorine and bromine. So it's a lot higher numbers, meaning they're a lot more likely to happen. So that's where the n+2 and an n+4 peak come from, is from the isotopes of chlorine and bromine. So we can actually very quickly identify a molecule as having chlorine or bromine based on looking for specific patterns. Because of the relative abundance of chlorine and bromine are very specific and they don't change, right? We have a 75-25 split for chlorine, 50-50 split for bromine. We are going to get very specific splits when it comes to these elements. A molecule with chlorine, that chlorine can either be chlorine 35 or chlorine 37, and if there are 2 chlorines, if there's only 1 chlorine, then we're going to get a 3-to-1 height, meaning that the n+ peak height will be 3 versus the n+2 being 1. So we're in a 1-to-3 ratio. The n+2 peak will be 1/3 the height of the n+ peak. Why is that? The 3 representing the 75%, or the 1 representing the 25%. So essentially 75 to 25 ratio can be simplified as a 3 to 1 ratio. So 75% to 25% can be simplified to a 3 to 1 ratio in the heights of the peaks. And I'm going to show you what these look like in a second. With bromine, though, because they're 50-50, you're going to get the M plus peak and the M plus 2 peak being identical in height. Because half of all of the bromines in the universe are 79 and the other half are 81, when we look at the M plus 2 peak, which is the one containing bromine 81, and the M plus 1, or the M plus peak, which is the one containing bromine 79, because these are both as likely to happen as each other, we have a 50 to 50 ratio, meaning that their abundance, their height, is going to be a 1 to 1. Now, things get a little more complicated when we have 2 chlorines or 2 bromines. And that's because when we have 2 chlorines, we can have 3 different combinations, 35 and 35, 35 and 37, or 2 37s. Because the 35 chlorine is 75%, whereas the 37 chlorine is 25%, the chlorine with 2 35s is going to be the most likely to happen. So I have a height of 9. The chlorine with 1 of each is going to be a little less likely to happen at 6. And then the chlorine with 2 37s is going to be the least likely to happen at 1. Why is this? This is because of statistics, right? Whenever we look at these ratios, we need to consider the chances that both of these will happen. So these being 75% each, that's 3/4 times 3/4, we have 0.75 times 0.75 chances that this particular combination will happen. Whereas this particular combination has a 0.75 to 0.25. And then this is 0.25 to 0.25. So they're less likely to happen. And I'm not going to go into mathematics because they're not really important. But the split here, if we have chlorine in our sample, if we have 2 chlorines in our sample, we'll see a 9 to 6 to 1 height ratio between the M plus 2, and M plus 4 peaks. With bromine, because of 50-50, the one that's the most likely to happen is actually the combination where both bromines are 1 of each, 181, 179. So with the bromine, the splitting pattern we're going to see between the 3 peaks is a 1 to 2 to 1 ratio. So let's actually look at them to make this make a little more sense. Let's start with the simple ones. Let's say we're looking at the mass spectra of chloroethane. Chloroethane, remember, is just a 2-carbon with chlorine, right? So 2-carbon carbon chain with a chlorine on it. This chlorine could be either chlorine 35 or it could be chlorine 37. Because of the ratios, this compound is 75% of all the chloroethane in the universe and in your sample, whereas this one with the chlorine 37 is 25%, because those are abundances of those isotopes. Meaning that if we look here towards the end, we're going to see the M plus peak, and remember that's going to be the highest one towards the right. So we see here, this right here is the M plus peak at 64, because the molar mass of this is 64 grams per mole. And then 2 down from that, we see the M plus 2 peak, which has a molar mass of 66 grams per mole, because the chlorine here has 2 more grams per mole than the isotope chlorine 35. So what happens? If you look at the heights, this one is roughly 1/3 the height of this one. So we'll call this 1/3 X versus this being X. Or, if we wanted to put a ratio, a 3 to 1 ratio between the heights. So by looking at this, if we didn't know what this was off, which compound this was off, by looking towards the end, identifying the M plus peak and the M plus 2 peak, and then looking at the height difference, then noticing that it's a 3-2-1 height difference, we would know that this compound has chlorine in it. And it has one chlorine specifically. If we look at a sample for bromine, there you go, M plus 1. Well, the M plus 1 is a little shifted. The M plus 1, and ignore this. I don't know why that has shifted. The M plus 1 is actually this one right here, not this one. This is the M plus 1 peak. So if we look at our next one, this is for bromoethane. So same molecule, 2 carbons with a bromine instead of a chlorine. But again, there are 2 different options when it comes to isotopes. There's the bromoethane with bromine 79, and there's a bromoethane with bromine 81. This one would have a mass of 108 grams per mole, whereas this one has a molar mass of 110 grams per mole because of those 2 extra neutrons. And now if we remember, because bromines isotopes are a 50-50 ratio, both of these compounds are as likely to happen. Half of the bromoethane in the universe is bromoethane 81, and the other half is bromoethane 79. So when we look at the peaks here, the M plus and the M plus 2 peak, they are almost the same height. And I say almost because remember, this is not going to be ideal. This is not going to be perfect, right? So we need to take this with a grain of salt. Notice that the M plus 2 peak is slightly lower because of statistical anomalies and error than the M plus peak. But they're roughly the same height, meaning that just by looking at this, not knowing which compound this belongs to, because we see that M plus and M plus 2 peak being almost identical in height, we know that this compound is very likely to have 1 bromine in it. And we just tell that by these patterns. Like I said, we can also see these patterns with things that contain 2 chlorines and or 2 bromines. If we look at 1,2-dichloroethane, which again would be a compound where we have ethane, so 2 carbons, 2 carbons, and it's 1,2-dichloro, meaning we have 2 chlorines, 1 on each carbon. We have, again, 3 different choices when it comes to these chlorines. The M plus peak is going to consist of the molecule where both chlorines are chlorine 35. They have the exact same molar mass. The M plus 2 peak is going to be made out of 1 chlorine being 35 and the other chlorine being 37 in the molecule because it has 2 more neutrons, therefore molar mass is 2 higher. And then the M plus 4 peak will consist of the compound where both of the chlorines are chlorine 37. And these are going to come in a very specific ratio. Whenever we have 2 chlorines, we're going to see a 9-to-6-to-1 ratio between the 3 peaks. So here we can see, and you got to be careful because you might think that this is the M plus peak. And even though that's the biggest fragment peak, the 3 peaks are actually right here at the end. We have our M plus peak, M plus 2, and M plus 4. Don't be fooled by this very large peak. Notice how there's peaks much higher up than that one. So these cannot be the M plus peaks. M plus peaks have to be very close to the end, with only M plus 1, M plus 2, and M plus 4 peaks being higher in most common spectra. But if we look at these, we have that 9-to-6-to-1. So we're going to have the M plus peak. The M plus 2 is roughly 2/3 the height of that one. And then the M plus 4 is very small. It's roughly 1/6 of the M plus 2 peak. If we see this pattern, it's kind of like descending bars at the M plus 2, and M plus 4 peaks. We know that there's 2 chlorines in our compound. And then finally, let me zoom this in. So here you can get a better idea of that 9-to-6-to-1 ratio. So you can see 2/3 this one of this one, The n plus 2 is 2/3. And then the n plus 4 is like a sixth of the n plus 2. Now the last ratio you should be able to identify is one where we have two bromines. When we have two bromines, again, and this is 1,2-dibromoethane, so exact same molecule but with bromines instead of chlorines. So I'm going to draw them here real quick. Br. We're going to have three options as far as the isotopes here. We have the 1,2-dibromoethane, where both of the bromines are 79. The 1,2-dibromoethane, where one bromine is bromine 79, and the other was bromine 81. And then the last one, where one bromine is or actually both bromines are bromine 81. This is going to consider the N plus peak, because it is the lowest of the three. It has the lowest numbers. This is the N plus 2 peak, because that 81 raises our molar mass by 2. And this is the N plus 4 peak, where both those 81s raise our molar mass by 4. Because of the 50% between carbon 70 or bromine 79 and bromine 81, we are going to get a 1 to 2 to 1 ratio between those peaks. So if we zoom in here, we can see, I mean, they're very small, but these have to be the N plus 2 and N plus 4 because they're so far to the right from these bigger peaks. But you can see that 1 to 2 to 1 ratio in this mass spectra. We can see how 1 to 2 to 1 in height, because these are roughly the same height, and this one's roughly twice as big as the other two. Ignore this right here. This is just noise, is what we call it. It's an interference signal. But we can see that 1 to 2 to 1 between N plus 2, and N plus 4, which is going to give us that idea that this definitely has two bromines in it. So that's it. That's it for our mass spectra for our organic chemistry or organic compounds. I would highly suggest that you go back to chapter 3 and watch the video on mass spectra to remember how exactly it works. But this is how it works. Exact same technique, exact same machine, but how it works on organic compounds and the fragments that it creates and all that. So that's it. That's it for chapter 18.8, I guess, or maybe chapter 3. Whatever the last section was. But this is also it for the whole curriculum. We've done it. We've gone through every single topic in the AICE chemistry curriculum. And now all you have left is to study and review everything we have covered this year. Good luck on your exams, and I'll see you in A-level chemistry.